Hey gang, welcome back. This is our third in a three-part series on confidence intervals. We started out talking about confidence intervals very broadly. Then we talked about calculating exact confidence intervals using a table of z-values where we were drawing from the standard normal table. And in this last slide on confidence intervals, we're going to actually drop the use of the standard normal table and venture out into completely new territory when we're not dealing with normal distributions. Essentially, it's what we're going to have to do in practice, in real life, when you don't know much about the population, you don't know the mean, and you don't know the standard deviation of that population. And when those two things happen, you need to use the student's t distribution. So before, this is how we calculated a confidence interval for the mean. We constructed a bound around x bar. So we added and subtracted a margin of error. And this whole thing is what we called the margin of error. Now the margin of error really consists of two things. It is a certain number of standard errors. Like that. And the challenge really wasn't just plugging in values in for sigma because that was given to you or the sample size or anything like that. The challenge was in figuring out how many standard errors do you need to bracket around your mean to get a 90, 95, or 99% interval. And like the name here kind of indicates, is we were drawing from a standard normal table. The thing is, what if we are drawing from a normal population, but we don't know what that parent population's standard deviation is? Now this is perfectly logical. If you don't know what the mean of the population is, what makes you think you would know the population's standard deviation? I mean, that's a trickier concept, right? If you were going to know anything about the population, you'd have a pretty decent handle on what the average is. But that standard deviation for the population, it's unlikely you would know that. So this is definitely more of a real-world practical kind of thing, is constructing this new type of confidence intervals. The problem with not knowing sigma is that we have two sources of variation. We have random sampling bias, because we took a random sample to calculate x bar, but we also have random sampling bias when we have to estimate sigma with the sample analog, with the sample standard deviation, S. So since we have two sources of uncertainty, we're extra uncertain. And essentially what we need to do is modify our normal distribution to kind of capture that uncertainty. So if you think about your standard normal, it looks like that. But we want to somehow show that we have a little bit more uncertainty. So what we need is more probability in the tails, because it could be way to the left or way to the right. And it's less kind of clustered around the middle, which would indicate certainty. We want less certainty. So that spread has got to get wider. So what we need to construct then is something kind of like a normal distribution, but that's less clustered around the middle and has more probability out in the tails. And it has to do that in a way that reflects how certain we are by using a sample. If we have a really, really big sample, then we have, we're on much more solid ground about what our guess about sigma is using our sample standard deviation, right? So large samples would indicate less uncertainty, and so we would use something more like the red line. But if we have more uncertainty because we have small samples, then we should be pulling from something that looks a little bit flatter, something like that blue line. And it looks like a normal distribution, but it isn't exactly. It's a close cousin of it. The distribution that we're talking about is actually called student's t distribution. And here's a really quick rundown about who student was. Student was actually a guy named William Gossett. He was a master brewer for Guinness breweries, like the actual Guinness breweries. And this was back in the late 1800s. And he was also like a super, super smart guy and a statistician. And essentially what he was doing was quality control for Guinness breweries. He had a pretty good idea that the distribution of, now I forget now whether it was barley or alcohol content or something like that, but the quality of the batches of Guinness was roughly normally distributed, but he wanted to know whether a particular batch was made properly. Did it have the rate, like the average amount of wheat that he was supposed to have on average, or the amount of alcohol that it was supposed to have on average? And but he was also limited to very small sample sizes because he had these huge bins, right? And all of the Guinness was made in like a small handful of these big bins. So it's not like he could rely on the central limit theorem to test out dozens upon dozens of these big giant stills where they were like brewing the beer. He had a small number. And so he actually worked out the math where he could test probabilistically the quality of his batches of beer. And so he came up with like this whole new distribution, and he wanted to tell the world. So he wrote up a scientific paper and he sent it off. But the thing was, is he was kind of like bound contractually to Guinness to not reveal trade secrets. So, other breweries could copy their quality control methods. So he wrote it under a pseudonym, and he called himself Student because he thought of himself as a student of statistics. He called this distribution the T, and so people started calling it Student's T distribution. And now we know that that student was William Gossett. So this is like actual practical statistics developed by an industrial statistician who liked beer. So maybe that takes some of the edge off on learning this material. So the T distribution is related to the standard normal. It has the same shape. What you'll see is that this top line here, the one that's in the small dashes here, let me switch colors. So this guy here on top, that's your normal. And notice it goes down. So it has very low tail probabilities and much higher central probabilities. Now the normal, you'll remember, is a whole family of distributions. Right. So we would talk about normal, and then they could differ by having different means or different standard deviations. And one of these was the normal 0, 1, what we call the standard normal. The T distribution is related to the standard normal. The T distribution is similar to the standard normal, but it actually depends on an additional parameter, something called degrees of freedom. Now, I won't exactly explain in this slide what degrees of freedom, or in this whole presentation what degrees of freedom means, but there'll be another video explaining degrees of freedom. For now, just know that it's a parameter, just like mu and sigma, and it's defined in this context to be equal to the sample size minus 1. So the T distribution itself is not independent of the sample size that constructs it. The normal is. The normal just is what it is, and you draw a sample from your normal, and the size of the sample doesn't change anything. The T is different. The T is designed to be a sampling distribution, and so it depends on the size of the sample in this particular way, this n minus 1 way. And what's the relationship between the T and the standard normal, between this guy here, standard normal, is that as the degrees of freedom increases, so we go from 5 to 10, to 20 and so forth, this curve starts going up and up, and eventually it asymptotes until it is really indistinguishable from the normal. So the tail probabilities shrink, the central probabilities rise until these blue lines look just like the red line that's the normal distribution. So in the limit, as the sample size increases, there's no distinguishing between the T and the normal. So the t is particularly suited to small sample sizes. And if you've got a huge sample size, you can still use the t, but it's also doesn't matter if you just switch over to the normal because you're splitting hairs by that point. So how do we use this t distribution to construct a confidence interval? The formulas between the two approaches are nearly identical. In this first line, I show you how to construct a confidence interval for the mean when we're pulling from the standard normal. And we do that when we know what the population standard deviation is, when we know what sigma is. In practice, we don't know sigma, so we have to estimate it using the sample standard deviation. The instant you do that, you can't use z-values anymore. The instant you have to resort to a sample for your standard deviation, you need to switch over to a t distribution. You can use Excel just as easily for t distributions as you can for normals. So the computation isn't difficult. The hard part is just remembering which case you're in. And it's honestly fairly simple. If you remember that if you have to estimate an S, go for a t, you're good to go. So the real world practical thing is if you got to estimate the standard deviation with a sample, use a t distribution. Right? The practical student's t from the industrial brewer kind of guy. Now, as I said before, if you've got a huge sample size, you don't really lose anything by resorting to the central limit theorem. Everything is going to be normal. The t looks indistinguishable from the normal, and you can just go either way. It's always easier to understand things by example, so let's do one made-up example. Let's say that we wanted to construct a 90% confidence interval for football player weights. I don't know whether these are NFL or whatever, because I made up these numbers. But let's suppose that we draw a sample, and we know the sample is normal, but we don't know anything more about that. We don't know the mean of that distribution. We don't know the standard deviation. So we collect a sample of 25 players, and from this sample, we calculate a sample average of 260 pounds and a sample standard deviation of 35 pounds. Since I had to use the sample standard deviation, I know that we need to use a t distribution. So how do we construct this confidence interval? Just like before, our best guess is still the sample average, but then around that, we want it plus and minus a margin of error. That margin of error is a certain number of standard errors. Standard errors are going to be estimated now. It's usually sigma over square root of n, but now they're going to be s over square root of n. And now we need to figure out what is this certain number. And that's going to be, rather than z upper and z lower, rather than being a z statistic, it's going to be a t. So this is how we would construct our confidence interval. I know S, I know N. The part that I don't know is this T. But conceptually, it's the same exact thing as before. We've got some distribution. It just happens to be a T now. And we want a 90% confidence interval, which means we want some values that are symmetric, where so they equally bound on the left side and the right side of our best guess, so it's symmetric around our guess, and we want it to cover 90%. So that interior probability there is 90%. Now if 90% is in the middle, is shaded, then that means 10% is unshaded. But that 10% gets split up 50-50, here and here. So 5% is in that unshaded area, and 5% is in this unshaded area. And now we have our T upper and our T lower. And we just need to use Excel to tell us what these T's are. Now, Excel is great at telling us left tail probabilities if we just do one of those inverse calculations. There should be a link somewhere up on top reminding us how to do inverse calculations, and I'll show you here in a second in the case of the t. Now, Excel tells us what is the probability that a particular random variable is less than some value, and it gives us a probability. That's the straightforward calculation. And that probability is 90% plus the 5%. And if we want an inverse calculation, we tell it all this, and we ask it to give us this value. So we just need to do an inverse calculation on a t in Excel to give us t upper. That'll immediately tell us t lower, and we can just plug that into our formula. Let's switch over to Excel now and calculate t upper. So here we have Excel. We just reminded ourselves what the question is. We want Excel to tell us what t upper is, so that's an inverse calculation. Before, we used to do norm.s.inverse or norm.inverse if we were pulling from a non-standard. Now we're going to do t.inverse. Open parentheses, and Excel prompts us what probability. It's 95%. And then it also prompts us for one more thing. It asks what's the degrees of freedom. Well, we had a sample size of 25 players, and the degrees of freedom is going to be 1 less than that. So it's 25 minus 1, or you could just type in 24. Close your parentheses, and we have our answer. It's 1.711. Now, what if we had done the, if we tried to calculate t lower? Well, t lower only covers 5%, that unshaded area. So t inverse 0.05, and then we would have 25 minus 1, or 24, and we get the negative of that. So 1.711, let's call it. All right, so 1.711. 1.711 is t upper, and t lower is negative 1.711. Oops, 1.711. All right, so let's key this into our confidence interval formula and get our answer. Our confidence interval is 260 plus and minus our t-stat, which is 1.711, times the standard error, which is s divided by the square root of n. S is 35. N is 25, so the square root of 25 is 5. And that's our confidence interval. We can key that into a calculator and get a result. Okay, so we key that into a calculator and we get 248 to 272. That is our confidence interval now for what we think the average football player weight is in this particular population. Our best guess is still 260, but it can be a little bit more or less. We're going to go between 248 and 272 for the average weight of the entire population of football players we sampled from. All right, we're going to do a couple more examples. In the second example, we're going to draw a small sample from 20 people. We're going to draw it from a normal population. We don't know what the population standard deviation is, so we're going to need to use that. And since we're going to use the sample standard deviation as a proxy for the population one, we've got this second source of uncertainty. We're going to have to use the t-distribution to construct this 95% confidence interval. So what value for t do we need to use to construct our 95% interval? Remember, our interval is going to be our estimate plus or minus some margin of error. That margin of error is going to be a certain number of standard errors. So we need to know what this certain number is that matches up with 95% confidence. So the process is just like with the normal. We have some kind of bell-shaped curve, and we need two values of t, a plus and a minus, t upper, like Tupper, and t lower, where the area between them is 95%. Now if 95% is in between these lines, that means there's 5% unaccounted for, and it gets split up between these two tails. So 2.5% is here, and 2.5% is there. Now Excel only gives us left tail probabilities, not between 2 points probabilities. So we can just tell it what's the value of t that accounts for 95 plus 2.5%, so 97.5%. So we just need to open up Excel and key in an inverse calculation for 97.5%. Let's go do that right now. Okay, so we want an inverse calculation. So t dot inverse. We specify the probability, and then we need to tell it the degrees of freedom, which remember is 1 less than the sample size. So if we sampled 20 people, then we need 19 as our degrees of freedom. We could put 20 minus 1, or we could just put in the 19. Either way. Hit enter, and this is how many multiples we need now. And notice that this is also close to 2, which is what we had used normally, see what I did there? When we were talking about a 95% confidence interval. When we were using the normal curve, it was a little bit less than 2, it was 1.96. Now, with this t with 19 degrees of freedom, it's a little bit above 2. So notice that it's a slightly broader range. Okay, so that's how many standard errors we need to go above and below to create our confidence interval, our 95% confidence interval. So let's use this number in our calculations. Let's switch over right now. So t upper was 2.09. T lower must be negative 2.09. And our interval is x bar, which is 32,000, plus and minus our margin of error, which is a certain number of standard errors. That number is 2.09. And then our standard errors, normally we would do that, but since we don't have sigma anymore, we're going to do this. We're going to use our sample standard deviation. So we have 5,000, and then we divide by the square root of 20. So this is our confidence interval. Let's key in those specific numbers so we can get our final answer. So after we key that into our calculator, we're going to get a confidence interval of 29,660 to 34,340. Okay, so that is our best guess for average income from our population. Not the best guess for any one particular person's, but it's the average, our best guess for the average of the population, 29,000 to 34,000. In this third and final example, we're going to construct a 99% confidence interval. We're going to use the t distribution, and the confidence interval is for the average number of raisins in a cereal box. So let's say that you took a sample of 10 boxes. You believe that the raisin distribution is normally distributed, but you don't know whether it's its average or its standard deviation. But you take that sample of 10 boxes, and from that you have a sample average of 310 raisins and a sample standard deviation of 25 raisins. Let's construct a 99% confidence interval. So all the confidence intervals have the same pattern. It is your point estimate plus or minus margin of error. That margin of error is a certain quantity of standard errors. And the big question is, what's that quantity associated with a 99% confidence interval? with a sample size of 10. So we draw our t-distribution just to kind of guide our intuition. We're trying to find t upper and t lower, where the area inside between those two t's is 99%. Now, if 99% is inside of that bounds, then 1% has got to be outside of that bounds. And it's split evenly between the right-hand side and the left-hand side. So 1/2 of 1% is here, and 1/2 of 1% is there. Which means this particular t upper accounts for 99.5%. Probability is less than t upper. So we can just pull up Excel and have it calculate the t upper that gives us this probability, an inverse calculation. We'll switch over right now. So here's Excel, and we've just repeated our data for that problem. And we want Excel to tell us what is t upper that gives us this probability. So t dot inverse, we give it the probability, it's 995, and then the degrees of freedom is n minus 1, so 10 minus 1, or 9. We hit enter and we get 3.25. So that's our t multiple. So how do we construct a confidence interval around x bar using this multiple? Our confidence interval is x bar, that's 310, minus 3.24 standard errors. So we can just key A 6 times the number of standard errors. That standard error is sample standard deviation divided by the square root of n. So that's 25 divided by square root of 10. So that's our lower bound. Our upper bound is 310 plus this many standard errors. We just do A6 times 25 divided by the square root of 10. All right, so those are our confidence bounds, our intervals. We have essentially 284 to 336. If we go back here, our confidence interval is 284 to 386. And that's our confidence interval for the average number of raisins in the box. So, you know, even though we happen to take a particular sample and our sample average was 310, if we want to be 99% sure that we've captured whatever the true population average number is, we think it's going to be somewhere between 284 and 386. All right, so let's just retrace our steps. What have we learned? We've learned that we have to modify our confidence interval formula when we don't know what sigma is. The instant we don't know what sigma is, when we have to use the sample standard deviation as a proxy, then we need to make one other change. We need to use the t-value statistics rather than the z-values. So we're going to have to not just plus and minus 1.96 standard errors from the mean, but actually a little bit more. And this t-value, eventually, if you have a large enough sample size, it becomes indistinguishable from the standard normal, but for smaller sample sizes, that difference can be noticeable. So you're always correct to use the t-value if you're using an S. And the way I like to think of it is, if you're using S, then T, right? Alphabetical, S, T. You can get away with using a Z if your sample size is large enough, but you'll always be safe if S, then T. Okay, so that's it. I think you can now tackle a whole range of confidence intervals problems, whether you're using the population standard deviation and a Z, or sample standard deviation and a T. All right, thanks for listening. Bye-bye.